Alright, in this video I'm basically going to take a look at the basic buck converter here and just the basic little circuit theory. And I did make an observation here that that basically if you have a 100% duty cycle, this kind of is exactly the same kind of circuit you might have in an analog power supply, particularly the older ones they used to use inductors in. I mean, it's exactly the same circuit, more or less. You'd have a, feed in from your bridge rectifier circuit out here, and of course that'll have, that'll be a pulsed waveform, not a straight DC waveform like you get here. But, that's fed through an inductor, and, then you got a capacitor here, and basically it acts like a second order filter, in order to, with a component size to try to filter out the ripple. So, and again, they, will often have pi circuits and stuff like that in there, something not this simple, but the simplest form of it kind of resembles that. So, it's kind of a way of, thinking about an SMPS, to, take a little of the voodoo out of it. But basically, you do have a series resonant circuit here, but it's a second order filter, so it's acting as a low pass filter. Um, but because I was considering putting some inductors and some circuits in an effort to try to mitigate short circuit conditions, on your circuits to allow the your circuitry to kind of take care of it, buy some time for it, but really it wouldn't work because your capacitors would discharge. And I, noticed out on some forums some people were saying, oh, you'll form resonant circuits if you use inductors in it. And so I just never really investigated it, because again, I realized, well, it's not going to stop your capacitor from discharging, so your circuit's still going to go dead in a short circuit. So it's not really going to help much. But at any rate, it does, kind of resemble that, and that's a way, at 100% duty cycle like I have it now. So, but and I'm basically following, I'm going through this Electronoobs, um, which you can just Google Electronoobs, and he's got, a series of articles on, boost converters and buck converters, and because I think he covers, let's see, 3 articles on it. Here's the boost converter article, and he's got a buck boost article. Um, which doesn't seem to want to do anything. Okay, and I guess that's pretty much the set. But but he has an associated YouTube channel too, and so you can look up Electronoobs. He's got some pretty interesting stuff on here. Although, and this is his video on the buck converter, which isn't referenced in the article. So, but I will say, I did notice some mistakes here, and he did this like 6 years ago. I think he was still in college back then. But he does, cover some of the basic theory and stuff here, which is pretty interesting. The final result is that your output voltage equals the duty cycle times the, the supply voltage. So, which is its conclusion. But what's interesting is some of these circuits are Arduino based, so you get like an Arduino controlled, converter here, which is very intriguing, and it's got a little potentiometer so you can control the output and everything. So that's what kind of caught my eye about this. Is that it was Arduino based, but he does have other circuits here, and here's an extension of the Arduino with feedback, and he covers, a regulator IC, which these are like, I don't know, $1.80 a piece or so off of for a 3 amp regulator on Mauser, and variable. So that's kind of cool. I might look into getting some of those. But he also has a 555 version down here using it as a PWM circuit, but clearly there's no feedback here. So but still it allows you to more safely investigate it, because there is a threat. Remember, I made a number of videos about the dangers of inductors, right? And um, this if you make this Arduino circuit, you do still have a potentially you know circuit, because some of these things can get carried away. You end up sticking things in the wrong place or whatever, and this thing does have a feedback circuit down here, for this version of it. So, you're feeding that back into your Arduino. I mean, and the Arduino is connected to your PC. So, I mean, if something gets out of control here, like you end up with a short circuit across that inductor, I don't know, it might generate a high voltage that maybe some of this won't cope with, and maybe your capacitor's loose or something, and when that happens, so you have a short circuit on it, that causes your inductor to really shoot up, I mean, there are just things that could happen, so it makes me a little nervous to build the Arduino version, at least for now, without connecting, hooking up the 555 version, although, it's possible your power supply might not like it. That's usually a low impedance source, so it would probably eat up any kind of a pulse out of the inductor. But what worries me is this 100 millihenry inductor. Do you know how difficult it is to find a 100 millihenry conductor, that's capable of any kind of real current at all? It's like a $46 part on Mouser if you look into it. I don't know if I still have that here. But yeah, it's like a $46 inductor, to get an inductor. It's 100 millihenry at 1 amp. All the other 100 millihenry inductors, are way lower than that. So, and I mean, you're going to be stuck with about 40 milliamps DC current, so it's, I have a feeling that's a typo. I put a comment on his web page about, where the hell am I supposed to find an inductor that big? But if you watch his video...
Electronic project, you will definitely need more than just one value of voltage. A way to achieve this process is called feedback. If K
the inductor he uses...
This voltage divider will drop the voltage from a maximum. This is the and MOSFET. We should increase the PWM signal so we could maintain the Okay, so now we have the distance. In order to keep the output,
come on.
The only thing that changes, we set the desired voltage with the
Just hold on, let me. Okay, yeah, the circuit he's building, again shows a 100 millihenry inductor, right? So, okay, but let me ask you this, let's see, to me, I'm not so sure that looks like a 100 millihenry inductor, because that's got some pretty hefty gauge wire on it. There's not that many turns on that coil, and, but I can tell you, because of the wire gauge on that thing, that could certainly handle 5 or 10 amps, surely, and, I thought he had more of a close-up of that damn thing here, but I don't see it right off. I don't see a close-up of it, him showing that. He did somewhere in the video.
In the potentiometer.
But, God damn it.
Apply 12 volts to the input and start
But yeah, I mean, that inductor, it's kind of on the small side, but I mean, with that kind of wind, there's no way that's 100 millihenries. And like I said, to show you what a 100 millihenry inductor looks like, let's see. Hold on. So here's all the 100 millihenry inductors Mouser has. I'll sort them by price. And this includes out-of-stock stuff too. I mean, this isn't just what they have in stock here locally or normally stock. But if you look at them, these are all 100 millihenry. You know, let's see, 100 millihenry inductance. But if you look at the current, you know, that's what you're kind of stuck with. You know, 70 milliamps, not specified, 90 milliamps, you know, 70 milliamps. You'll find that a lot of these aren't in stock. But the only ones that actually get up to what you could use for a typical SMPS, or would use, you know, you could do this for a low current SMPS, I suppose, but it's got to be able to, the inductor's got to be able to handle the rating of your load, because sometimes the inductor supplies the load, right? So, you know, that's a pretty weak power supply. You know, you have much better luck getting, you know, inductors in the microhenry range. You know, you can get them easily and cheaply for 3 to 5 amps quite readily. But, you know, this 1 to 5 amp inductor, let's see, the 5 amp one's $113, and, you know, the, you know, 1 amp one is $42, and they look like transformers. You know, and that's what you would expect out of such a big inductor, you know. But again, if you're looking at relatively small inductors, you know, you're just not going to get very much current out of it. So that's got to be a typo. So, you know, and like I said, another issue too I've noticed on here, let's see, you know, let's see, source drain, yeah, that's, you know, he's got this, you know, wired appropriately for a PMOS, you know, a P-channel MOSFET. So that looks good. But see this, I'd have to zoom in, and you still, still can't zoom in on a stupid drawing. Man, fucking Google sucks. But this is actually the same transistor. But here, you know, he's got it wired backwards from what he's got down here. So, you know, he's got the source and drain, and that's how you should have a PMOS, you know, that's your power input. Because of its body diode, you know, this makes sure the body diode is reverse biased, right? If this were an N-channel FET, that's proper, you know. Well, no, even an N-channel, that's wrong. But for a P-channel, that's right. So, but up here, you know, you can see he's got it wired backwards. He's got this wired like an N-channel, because that's how you'd wire an N-channel device, but it's still a PMOS, you know, FET. So if you wired it that way, you basically have the body diode in forward conduction mode. So the transistor's not going to control anything. All the current's just going to go right through that body diode. So, you know, so at the very least, you know, you're not going to have any control of the circuit. So, you know, so there's things like that you got to kind of look out for in some of his stuff. And here he's got an NMOS chip, so that's like pretty damn similar to the circuit we're looking at down here, right? You know, drain, source, drain, source. So, you know, he's basically got the same circuit, he just labeled the transistor wrong, apparently. You know, but the thing is, you look at his symbol, well, that's the symbol of PMOS, you know, a P-channel FET. You know, so, yeah, that's P-channel FET. You know, but up here, you know, that's the symbol of a P-channel FET too. But it's a PMOS, so yeah, I mean, but again, it's backwards, so, you know, because like I said, he's wired this up as an NMOS, and if you look at his, you know, it's backwards there, and it's certainly backwards here, you know, because again, the source should be connected to the power input on a P-channel FET. That's definitely a P-channel symbol. But let's look at his video again, and see how he drew things. If I can find that schematic. Here. Okay, so see here he has an N-channel FET, and RFC44 is an N-channel device, but he still has it drawn as a P-channel. So, you know, but at least it's connected properly, you know. That's how an N-channel device should be connected: drain, source, and gate. So, but again, he's got the wrong symbol for it. That's a P channel. The arrow should point towards the, you know, towards the junction, towards the gate, to be an N channel symbol. So he's still got the wrong symbol on it. So again, his schematic skills certainly back, in those days weren't so great. But shit, this is a glorified fritzing diagram, for crying out loud. So who knows? I absolutely hate fritzing. I mean, that's just, you're not serious about electronics if you're drawing fritzing circuits. It's like you don't know how to read schematics, right? I mean, that's what I always thought, seeing those things. I mean, they're fine for helping people out that are new to it, though, so I'm not going to badmouth them too much. But shit, the program's not even free. So you can't download it anymore. I mean, I tried downloading it several times. No, they want you to pay them money for that goddamn thing. I ain't got to do that. I mean, I got way better software than that. You were drawing schematics. So, anyway, it's still, just be aware if you want to go through these tutorials that there are some anomalies here. And so be careful about that. But yeah, back to our little study here. Like I said, that's one observation I noticed about it, is that, this really is kind of like a filter circuit for a conventional power supply, from like the 70s or whatever. So that was an interesting correlation. But like I said, you back the duty cycle off, which you can in this. I was going to actually save this as a link. Let's go ahead and create a tiny URL here. Alright, so it's, well, let me just copy that to the clipboard and go over here and put it down in my little spreadsheet and blow that motherfucker up so you can see it. And there's what you type in, 26 GAJG7E. So, and I'll go ahead and put it here. So I can save it. Call it that, so I can recognize it instead of that cryptic bullshit. But yeah, so I mean, as you drop your duty cycle and everything, it changes, and you get this interesting waveform. That's why I wanted to analyze the shit out of it. Let me reset it here and just slow it way down. Okay, so this is basically the voltage, I'm measuring, across the inductor and across this wire too. I'm getting the current off that and voltage with it. But let me reset it again. Okay, so but basically, yeah, we're setting the inductor here, and this is the output voltage, so we're seeing the voltage across the capacitor. You can see it slowly charging up, and you can see where the current's flowing, which is going too fast. But, you can see the voltage. Well, let's reset it again, damn it. Okay, so you can see the inductor's got, 11 volts across it right now, and it's putting out 80 milliamps, and you can see the current is charging the capacitor right now this is the voltage effectively across the capacitor and the load, and that's the voltage across the inductor, so you can see what's kind of going on. At first it's charging the capacitor, but now now the thing is turned off, so you can see the voltage across the inductor here, has slowly declined, but now it's gone negative, for this cycle, and and it's in further decline. It's 3.8. Now it's switched on again, so it's up to 7 volts. 130 milliamps being delivered, but our capacitor is getting close to being charged up to its ultimate voltage, whatever that's going to be here. But you can see that basically, yeah, you get this voltage waveform here, and let's speed things up here so it gets up to operational levels. Alright, so basically you can see the current through the inductor and what it's doing, and it drops to 0, then you get this little notch here. Now, little notch means that the inductor is running out of juice. And let's see what happens when we change the frequency. Let me speed it up to see if I can accentuate that notch. Yeah, there we go. It's so you can see what's happening here. Basically, right now the pulse is switched on, and then it switches off really quick. And let me slow this down. So you can see, what the output voltage is right now where we have it, because again we're running at about 2 volts output. Let me speed it up just a little bit so we can study it. Okay, I'm probably sure the next pulse is about to come. So, you can see we're sitting here at nanoamp levels. That means the inductor is out of juice. It's not supplying any current right now. And you can see that stopped supplying current right about there. Alright, but our pulse is about to happen again. You can see the input pulse over here. That's going to turn on the MOSFET. So it's about to happen. There we go. Alright, so now our inductor, has 9 volts positive across it again. And we got mere millivolts on its input. But it's supplying 22 milliamps, as it's recharging the capacitor a little bit, which you can see is starting to happen down there. But then it's also supplying current to the load while it's doing that, because the capacitor is really just charging up. It's really not supplying anything to the load right now because it's being charged. It's part of the load, and it will be until it stops charging. But now our pulse switched off. Okay, now the inductor is still charging everything because its polarity has reversed. So it's got like 2 volts of polarity, which is a little higher than the voltage of our load. But again, it's still trying to charge the capacitor and the load, which 20 milliamps is going to the capacitor and 20 milliamps is going into our load right now. And it'll continue for some time until the inductor finally runs out of energy. So but its voltage continues to get more negative as it heads that way, because the capacitor is getting more charged up. So it's the inductor is generating more voltage to try to maintain whatever current it has, because its current demand is falling off. So it's negative voltage is actually getting higher as it tries to deal with that. So as our capacitor now is about reached full charge, so so the voltage output from that inductor has become quite high, but but our voltage across our load is still relatively low. But again, it's like I said, it's still got energy in it, and now its voltage is starting to fall because its current is finally falling off. It's about to give up, and now it does give up. It just ran out of energy. So, and it runs out of energy, this snaps to 0. We got 99 milliamps, nanoamps now, so it's really not supplying anything anymore. So it's just fully the capacitor now that is actually supplying the current. And again, this is one mode. Some people don't allow the inductor to run out of energy, so they'll keep turning it on well before the inductor runs out. So I guess that makes a smoother supply or something. I'm not really sure, but that's one of the 2 modes they run it in. This is the second mode where they do let the inductor run out of energy and the capacitor is on its own for a little while. So, until the next switch occurs, which it just did. Okay, so that charges up, starting out with 9 volts across it, which is falling, and it's trying to replenish the lost charge in the capacitor. So again, but it's actually supplying more of the load voltage at this point. Let me speed the current up a little bit. So you can kind of see what's going on, you know, but it's, you know, the current split about evenly, you know, between the capacitor and the load, but it's actually a little higher in the capacitor right now. So now the pulse is turned off, you know, because you know, the square wave has gone low again, so it's turned the FET off. So, but at any rate, you know, this slow motion kind of, because that's what's always puzzled me a little bit, is exactly what goes on here. You know, what goes on when this first turns on, and what happens during normal operation. I mean, how does the current interplay and the voltages across these devices change, you know, as the thing goes into the, you know, the high mode versus the low mode, you know, gate on versus gate off, you know, so that's what I'm kind of taking just a slow, close look here at the buck converter. But like I said, a buck converter is you know, good to look at because it bears some resemblance, you know, between old power supply filter circuits. So, you know, it's like a new use for an old idea, right? So, so anyway, I just wanted to cover that. Okay, so I went ahead and built up this, yeah, the 555 version of his regulator, but I only used 100 microhenry because that's got to be a typo. I didn't use this exact same FET. I actually bought, you know, really cheap, you know, MOSFET for it. That's like a 57-cent P-channel FET. Let's see. That's not it. That's not it. Yeah, who knows where the fuck it is. Motherfucker. Yeah, I bought this IRFP 9Z24, you know, NPBF or whatever from Mauser, and it's like I said, you know, they're pretty cheap little FETs. Actually, they're cheaper now than they were when I bought it. It was like 57 cents a piece now. You know, bought these several years ago. But yeah, anyway, I went ahead and built up this circuit, you know, just to test, play around with the thing, and you know, you can see the circuit here. You know, I got some scope probes hooked to the output of the PWM generator, because that 555 is rigged up as a PWM generator, and like I said, it can go up to about 100% duty cycle, but it can go down to like I don't know, 20% or so. So it's got that kind of restriction on it. But you know, I have my resistor decade box, so I can, you know, vary the load. And right now, you know, because again, the voltage will vary with the load, just like he says in his video. And my videos, by the way, aren't meant to replace his; they're just meant to augment his and answer some questions that aren't really shown in his video, and he didn't even do this circuit in his video. So, but yeah, there's basically the output, you know, that you can see, you know, kind of what's going on with it. The yellow trace is the output of the power supply across our load, and the you know, blue trace is our square wave coming out of our op amp being fed directly into the gate. That's why I'm measuring it. So, and there's the voltage, you know, where I got it set right now, and I can adjust this. I just put a 5K potentiometer in there. If I would have put a 50 in there like he had, maybe I could have gotten better range, but maybe not. Probably so, though, given the 1K he fed into this. You know, not really sure, though. It's kind of a balance point kind of thing, but you know, I kind of doubt it, but it might have made a difference. But let me try to rig this thing up so you can see what happens when I change the duty cycle on it. Let me put it, I'll put it there. If this doesn't fall on my circuit, it probably will. I'll show you. I'm going to go see the voltage now, as usual. see it there very well or not. Okay, that's got it, oh, that's good as it's going to get. But, I'll change the duty cycle and you can kind of watch the voltage. I can see a little better that way. Okay, try to get this screwdriver into this stupid thing. So yeah, that's the minimum duty cycle. So again, that's like 20% or so. But as the duty cycle increases, the voltage rises, of course. And again, that's almost 100% right there. So 7.9 volts. I got, it's being fed with 12 volts, as you can see there. From the power supply, and so I got a 300 ohm load resistor on it because again I don't want to. Well, actually, I got it set to 200 ohms. That's about the maximum I want to put on this because my decade box will burn out potentially. Although if the voltage is low enough, maybe not, but but that's going from minimum to maximum. Let me try it briefly. Yeah, 2.3 volts. Probably no problem. With a 100 ohm load on it, so I'll briefly take it up to maximum. Come on. Okay, yeah, it's probably fine. So again, that's this varying from 0 to 100%. Again, this isn't the same FET he used. The one he used was better. This one has like 120 milliohms RDS on. So his was like 20 milliohms, and was like a $1.80 for it. So that's why I bought the cheaper ones for these experiments. But at any rate, yeah. So I mean, again, you change the load. Like I just, upped it to 500 ohms. So you can see then that's the minimum voltage, and that's the maximum voltage. So at 9 volts. But yeah, it still seems to, work okay, I suppose. Get a lot of spikes coming off that, that square wave, that's for sure. But oh well, it's 555, and it basically shows you the principle. So, I mean, it would have been nice if I could have used a bigger inductor, because then everything would be slower and you could observe it. But this frequency of this is set about 2 kilohertz or so, 2.3 kilohertz. So it's a pretty low frequency deal, but it does show you the principle, of how duty factor, does, result in higher voltage. Although again, this thing certainly is not, getting up, to full voltage. So, the specifications are pretty simple or similar. The threshold voltage is -4 volts on both of them, and his MOSFET and mine. So, but yeah, I mean, there's certainly a voltage drop, and we're not drawing much current from this thing. Could take it back up to 1K. Okay, so now we're at 1.5K actually, and low duty cycle it's 8 volts. High duty cycle, it's about 9.6 volts. So I mean, it looks like about 9.6 volts is about as high as it'll get. So so anyways, this particular arrangement. So there you go. All right, I want to go and I'm going to take my one probe off the gate of the FET, I'm going to put it on the output of our 555. Take a look at that. Now that should be the input voltage. So, you know, like I said, that's outputting, you know, a little over, you know, just under 11 volts. So, and let me screwdriver here, because he says, you know, if you read his article, that the input range should be from 5 to 15 volts. So, you know, the VGS on this thing should be like 10 volts. So this might be right at the threshold. I'm trying to figure out why there's such a big voltage drop across the FET with 120 millivolts. Milliohms RDS on, because it may not be biased properly. Okay, so again, 9.66 volts is the, you know, highest voltage we can get, you know, the output. Let me go ahead, let's see what happens if I lower the voltage, you know, because again, you know, let's see if it can operate it down to 5 volts. The output has dropped to at 8 volts down to 5.8 volts. That's the maximum voltage at 7, 6, 5 volts. Okay, now let's see if that still is operating. 2.9 volts. The fuck is this so hard to get a goddamn screwdriver in? Minimal voltage, you know, like I said, it's 2.4 volts, so I guess it does give you some variability, but that's about to be expected. So let's go the other direction with it. Okay, got, you know, back up to 12 volts. Let's go 13, 14 volts. I don't want to go higher than that because, you know, the 555, you know, is limited to 15. But now here's like 11 volts. You know, is 11 and a half is the highest voltage you can get out of it, so it's dropping like 2.5 volts. You know, that's, you know, at the kind of current we're dealing with, that really kind of shouldn't be the case. Let's see if let me lower it a little bit, but that's not really gonna improve things much. Yeah, it just drops the voltage, of course. Right up 10K. Okay, 10K, we get 12 volts. You know, but again, yeah, I would expect higher output, you know, across that, you know, device. I mean, again, because, you know, that 555 should be dropping the voltage down, you know, really close to ground, etc. So, I mean, you know, it's like I said, it should have plenty of voltage to turn the gate fully on. But, you know, I mean, again, you know, this makes you wonder about the voltage drop, but again, you know, I mean, it is an inductor, and, you know, a switch mode power supply at the end of the day. It's not a resistor, so that's probably why, you know, that's why we're getting that voltage drop. But, you know, this is the output, not the input of the, you know, in fact, let me see if I can probe. Let me back it down to say for voltage for the 555. Let me see if I can probe the, you know, the actual output. Okay, the actual output across our FET. Okay, so, you know, that, you know, it's harder to read because, you know, you got all those voltage spikes in it. Let me go ahead and do this. Put this back over here. Let me take our meter and probe the voltage directly for kind of an average reading. I'm going to ride across the diode there. Okay, now it's putting out about 11 volts. And again, we're almost 100% duty cycle, so it's still dropping like a couple of volts across it. But I'm not really sure what kind of current we're talking about on average. I got to turn way up, so let me turn it down to a 400 ohm. Well, let me turn it down to a 300 ohm load. It should be alright for my resistance box. Yeah, that's like 9 volts with a higher load, so but again, I'm not really sure why it's dropping that much voltage across the FET, unless it's biased wrong or got something wrong with it. Cause I would expect it to be a little higher. I mean, it should have plenty of drive to turn it on. Of course, I got the thing, the duty cycle turned way down on the thing. Let me turn the duty cycle down. Man, this is bullshit. God damn it. Okay, I'll turn it down as close to 0 as I can get. I mean, it's going to give me kind of flawed reading, though. So I like to see it at 100% because we got a better idea that it should have a better turn-on voltage. But now we're getting like, only 5 volts now. So, I mean, it's, I'm not really sure what to make of that, but that's just kind of a little surprising. But again, there's probably a good reason for it. I just can't think of one right now because I didn't design this thing, so I had to really look into it closely to see, what's going on and with the FET and everything. But at any rate, I think that about covers the buck converter here. And like I said, I defer you to Electronoob's videos on the subject to see the Arduino version and everything else that he's got to offer on that. But yeah, I mean, I guess even Volstat has similar things taking place, so it's probably normal, I guess. Because here's a 1.5 volt drop. So anyway, I don't know. I'm just freaking exhausted. I've got kind of a bit of a hangover. Anyway, but I think that pretty much covers the basics of it. And takes a look at some of the things Electronoobs didn't in his videos. So again, it kind of augments, what's going on there. See, here we got more direct control over the thing because, because I can vary the duty cycle, much more generously, whereas I can only get it to, about here on this, but still, we can't do 100 ohm load on it, so, again, 300-400 ohms is where I had it, but, still, varying it down to like minimal duty cycle on this, which is way lower than we can go with the 555 circuit there. It gets it down to really, really low voltages, but again, this is about the lowest, we can go on our little circuit here. So, with that kind of load, still, that gets it up to about 11 volts, so, that's certainly improved, but this is an ideal MOSFET and, an ideal inductor, and, I think this rating on this inductor is like 3 amps, so it's not a high impedance inductor. So, but I don't know what the on resistance of this thing is. This body terminal bulk. Body, simulate body diode, okay. You know, I got it set to the wrong threshold voltage, but still. That's not going to make a hell of a big difference. Let me go ahead and change that to 4 volts. Okay. But still, I mean, you know, it's performing better than what we're getting. You know, if I take it up to a 1K load, you know, it's performing way better. I mean, you know, that's still, you know, within a small, you know, like 0.6 volts, you know, of the supply rail. So, again, a little peculiar. So, not really sure what to make of it. And of course, you know, again, at that level, at 1K resistor, you know, with the duty factor, you know, we can get out of a 555, you know, you can only go down to about 5.7 volts. Kind of similar to what we're seeing, you know, because like I said, I could go back to, you know, 1K load, and let me put my probes back in the decade box. So, you know, again, at the lowest duty cycle, we're getting 8 volts. You know, whereas fall stats, oh, well, we're not using a 100 millihenry coil. I forgot. I put it at that so I could actually see it more clearly. Because, you know, testing at 100 microhenry, it was doing shit that I couldn't actually see without increasing my step size and everything. I didn't want to mess with that. Let me reset it and see what our results are at 100 microhenry. But, yeah, it's still putting out at, you know, 11 volts at the same duty cycle, whereas we're only getting 8 volts. So, you know, so again, it's still a little interesting, you know, that we're getting different performance, but it's not the same circuit, though. I mean, obviously, I mean, he's powering his with a 555, and we're powering with an ideal, you know, square wave going right into it, you know, which is set to, you know, got set to 10 volts and, you know, offset properly, so it's, you know, on the right side. I would imagine, you know, if I took it to 11 volts, let's see what happens. Okay. Not really changing it that much. Let me take it to 12 volts. Not really making a huge difference, but it is. You know, it's you know, it's closer to the supply rail. So, no, I probably don't have it offset properly. But I don't know if that'll matter. I was adjusting the wrong thing. Okay, so yeah, with proper offset, you know, it's about still 11.5 volts, but still, you know, I don't know. I would expect it to be, you know, when I lower the duty cycle, you know, it's not changing much. So at 1K load, speed it up a little bit. Yeah, the duty cycle doesn't seem to be making a big difference at that level. It's like, not varying much even over the full range. So we kind of saw that, you know, with restricted range, you know, the higher the load resistance, you know, like right now I got it set at 1K just like in the simulation, and you know, shit. You know, we can go down to 100% duty cycle, we're like 10.4 volts, so, you know, versus 8.2, so we got a better range than we're getting out of the simulator. Of course, we're still at 13 volts, and we turn that down to 12. Alright, so, it's 7.5. So, versus 9.5, so about a 2-volt adjustment range with a 1K load, so we're getting better performance than we're getting out of the simulation. So, anyway, yeah, I'm not really sure what to make of that, but anyway. I'm still only so experienced with FETs in general, so. But at any rate, I think that, kind of covers the investigation. So, I mean, it's not off base for it not to go full voltage, but still, that's pretty damn close to full voltage right there. So, with 100% duty factor. So, again, we're not getting anywhere near that at 100%. So, but again, it is a different circuit arrangement, different source, so it might have something to do with it. I don't know. But anyway, this is just a brief investigation, so I just wanted to kind of check it out, because I intend to investigate this shit way more fully later, but it's just right now, it's just to kind of complete the whole study series, because this is the last thing I'm studying as part of the studies, and I just wanted to, this has been sitting around in a bag for, 2-3 years, and, I've been kind of wanting to take at least a brief look at it, so I figured, well, why not to cap off the studies, because I'm done with Malvino and, and all those books, so, this pretty much caps off our, videos related to that anyway, so, like I said the other day, I mean, I'm pretty exhausted. I'm kind of, electronics booked out right now, so, I need to kind of recover, because I've been doing this for like, I don't know, 5 or 6 weeks straight, for like 60, 70 hours a week, so, I mean, yeah, I'm a little fatigued, put out like all, did lots of videos too, and that adds fatigue, because I gotta go that extra mile, but still, hopefully this will, at least, if it doesn't do you any good, hopefully it'll at least do me good when I try to refresh my memory later. Yeah, I was kind of considering building his little boost converter, because it's just it's the same circuit, 555 wise, but it's just a rearrangement, uses RFZ44, which I got a bunch of, and, but the same coils, and at least he's calling it a 100 microhenry coil here, so, but, and you could use a 4001, because it's going to be the same 2 kilohertz duty cycle. A 4001 rectifier would work here too. You don't need a Shockley, not for this frequency. The problem with it is that it certainly occurs to me, like if we did what we did with the other circuit, the one that I still got running over there, that you can see, if we, adjusted it up to 100% duty cycle, well, basically this FET would be on 100% of the time, and basically, charging this inductor, well, at least up to the limits of the FET, which, that's like a, I think a 40 or 50 amp FET with a pretty low RDS on, so I mean, this could actually, that inductor is a 3 amp inductor, that I have. So, yeah, I mean, it could get some high current going through it, but of course, you can see right here, it would trip my power supply, because, I got the current limit set at about 75 milliamps right now. I could turn it up, but, it would result in a brownout, because I wouldn't want to turn it up. You start even at 75 milliamps, there's quite a bit of current. Could produce some, if something goes wrong, some major spikes in the circuit. Now, chances are the load itself would probably catch that. Not sure if it would damage the FET, but, but the point is that, I mean, it would brown out my circuit, probably put the FET, If it didn't brown it out completely, it'd probably put the FET, certainly in the active region, so it'd start dropping a lot of voltage across it. But again, if I limited it to like 40 or 50 milliamps, it probably wouldn't hurt it. But I don't think I want to mess with the headache, of that, especially given the results of this circuit, having some anomalies in it. But like I said, it would probably work. But like I said, I still think, well, even when I was trying to adjust that goddamn potentiometer, I mean, it's kind of loose in there, and it's just, I don't know, possibly a disaster waiting to happen. I don't know. I'm kind of disinclined to do it, but like I said, you can watch his video, and he'll do the Arduino version and so forth, and that would be worthwhile. And here's kind of what would happen, with the same inverter, and I got it set to 100% duty cycle, got a resistance pretty low, and basically you can see the FET stuck on continuously with 2 amps flowing through it, but it's still dropping 12 volts. So I guess however they designed this FET, it was not meant to handle very high current, because like I said, I don't really have a lot of adjustments I can make to it. Maybe if I adjusted the beta or something, but still their supply has infinite current capacity. So but it's basically just the inductor right now just has 100% current flowing. But then if you go turn the power supply off, then all of a sudden you're going to generate a spike, because you got at least 2.5 amps of current flowing through that coil, right? But again, that would be limited by my my power supply's current limit, but still, it could produce some high voltages and stuff, and I just kind of rather not mess with it. It's a boost converter, so it's sort of designed to generate higher voltages. But you can see right now, with the coil as it sits, it's in a pretty decent state. But see, if I turn my power supply button off, it has a capacitor in it, but it's actually still in a low impedance state, so it would still send high voltage through this thing. But again, it would, it's going to be dissipated on the load, because it's got 2.5 amps flowing through it, right? So, like, let's say I had, and again, I'd be kind of limited to probably 400 ohms or so, at most, at a higher voltage, for tests. So you got 2.5 amps flowing through a 400 ohm resistor. So that's 1 kilovolt it'll try to generate. So coupled with whatever residual voltage is on the power supply itself, because again, that'll become the negative, that'll become the positive. So if you turn the supply off, well, your FET gets shut off. So again, it's a recipe for disaster, and potentially. So I would kind of rather not mess with it. It's a great example of how some circuits with inductors, you always got to proceed with what can go wrong. What risk are you taking messing with it? And again, we'd only be dealing with 75 milliamps, but okay, for example, where I have it set now, but 400 volts times 0.075 would generate about 30 volts, okay, which, isn't terrible, but, if that gets coupled into the gate, well, it'll blow the gate out of the FET, that's for sure. And it very well might, that very well might just happen, through the chip, because, I mean, again, that's part of its, impedance circuit, especially if the supply were just simply disconnected. Okay, this inductor is going to try to discharge through the 555. So, yeah, I mean, it's probably going to hurt something, even with restricted current. Now, if I restricted it down to 55, you see right now it's drawing 27 milliamps where I got it now, so I'd probably want to put it at least 50, because it's probably going to require a higher current, right? So to me, it's not really worth playing around with, because especially in a breadboard, I mean, a lot of shit can go wrong. Like I said, that the potentiometer I keep having trouble with, sometimes that comes loose, and well, then things go a little bit haywire, the frequency picks up, etc. So I mean, to me, it's just kind of not worth the headache, you know, given the practical dangers involved in it. And again, this whole thing is something I intend to investigate, you know, in the future anyway, when I get more towards that, um, you know, move more in that direction later on, because, let's see, because I did have some interesting switch mode power supplies like this one I found, you know, I guess off that website, which is very intriguing. I mean, a 2 to 28 volt, 60 milliamp to 15 amp DC to DC converter, which can be in constant voltage or constant current mode. You know, it's a buck converter, but, you know, 12 to 30 volts in, so, you know, you can adjust the current here and, you know, and adjust the voltage here. And I already bought all the parts. The only thing I couldn't really find, you know, is this 80 microhenry inductor, and, you know, for 20 amps, so I figured, you know, have to roll my own. Problem is, I'm still not really sure what kinds of core materials. I figure, you know, I could take a, you know, a core out of a, you know, SMPS transformer from a PC power supply, you know, and because those are gapped cores, so, you know, they'll resist saturation, and they got the right basic materials in there for this. So, you know, you could wind that, you know, possibly an inductor around a core like that. You know, put it on the bobbin, though. You want to keep the, you know, some kind of bobbin. You know, you don't want your wires right up next to the core, just because of the capacitance, you know, increases like crazy when you do, and that has ramifications. So, for any transformer, really. But at any rate, you know, yeah, I already bought all the parts. I mean, they've been sitting in a bag for, you know, 2 or 3 years, and, you know, I had some other power supplies I was going to look at too. You know, that I bought the parts for. One in particular was out of Payson. Let me see. I don't know if I have those switch mode power supplies in here or not. Probably not. Hold on a sec. Yeah, here they are. Let's see. This is let's see what this one was. You know, I haven't designed circuit boards for these or anything. That's why, and these are complex enough where they pretty much demand circuit boards. I think this is one off Cassian. You know, Cassian TV, which, like I said, has a lot of interesting little circuits like this in it. You know, I've certainly built some of their circuits, and they generally work, I suppose. Anyway, that was one I was going to look at. Let me close this. See, DIY simple inverter. I was going to look at this. You know, these are all, I've already got all the parts bought and bagged up, but I just don't have circuit boards for them, and I haven't had the time to mess with it because they still are academic, you know. This too is off Cassian. So, you know, just enter Cassian and DIY simple inverter, right? You know, you'll find it. Now here's the web page. Let's see what that looks like.
Hi friends! Recently I saw an AliExpress board on the basis of which you can build a boost.
You know, it's Cassian TV, so, you know.
It's converted from 20 volts to these components. The converter has 150 watts output. It could be increased.
150 watts. With their nuclear vessels. Nuclear vessels. Anyway, but yeah, so Cassian TV is pretty cool. But, you know, yeah, that was one of the other little ones that I got bagged up because I already got parts for all these. Let's see what this one is. Probably another Cassian TV supply. It's like a pulse power supply. So, again, but I just never got around to designing the circuit boards and stuff. So, you know, here's that one I just showed you. So, oh, and here, well, I guess you can just go to the site, you know. I said, here's their site, you know, link to their site, but, you know, you can see what they're, you know, just enter that, you know, that URL, Electro Noobs, we've been looking at that. This is a 317 based power supply off somebody's channel. That's using the 317 as apparently a variable output switch mode power supply, which is intriguing. Let's see. Yeah, it's probably another Cassian TV thing, I'll bet you. Let's see if it is or not. No, it's not. Oh, yeah, it is. It's a Cassian TV. It's an AKA Cassian because he has 2 channels, so so it's not a Cassian TV, but it's still one of his sister channels. So he has a video on it here, so you can check that out. Let's see. But yeah, most of these, designing circuit boards is certainly in order. Especially for the reasons I just mentioned too. I mean, you'd be better off with a circuit board. I don't know. You might want to make the JFET or the MOS or the MOSFET, on a socket or something. You can just take a like an IC socket, and actually use snippers to snip off all the pins you don't need. So you can just snip off all but 3 pins and solder that into your board, and that makes a convenient little socket, for socketing things like transistors and stuff that you may want to remove. So that's a little trick, you may want to consider. See what this one is. This looks like another Cassian TV thing. This looks like a regular analog supply. So he does have a lot of just analog supplies on his site too. I've even built one of those. Let's see. Stock PWM regulator. Okay, I actually have a PWM regulator chip in stock from a long time ago. I guess I wanted to play with that. But it just didn't look very interesting. So I mean, I never got really around to messing with it much, so I was just going to build a generic circuit. At the time, I didn't understand PWMs very much. That's what I have an interest in them, because they are fascinating how they work. Here's, I think, another Cassian, too, about switch mode power supply. Yep, aka Cassian. So, I don't know what this is. It's way more complicated, whatever it is. So let's see, and I guess that's probably I don't know what all this crap is. Let's see what pictures we have. Okay. This is from an interesting website I found that had a lot of inductor detail, kind of obscure. Forgot where they were. I got a bookmark somewhere. Solenoid inductance calculator. Okay. That is. Oh, this is off of Vienna Electronoobs right there. So anyway, the fact of the matter is, though, yeah, I have a lot of. I guess I don't have the the Hazen circuit on here. For some reason, it might have actually gotten a project number. Yeah, I'd have to look it up, but it was actually pretty impressive too. Let me see. Shunt diode, linear ramp generator. No. Yeah, I don't know. I mean, I got it all bagged up, but I mean, I must have put that somewhere else. I'm not really sure. I doubt that's here. That wasn't a high priority project. Let's see. Thermal imager. Well, anyway. Hold on. yeah, it's probably one of these. It's a project number 100, so, but I don't have an actual official folder because I never did a circuit board, you know, because there was two of them in here, and, you know, this one can actually put out some pretty good current. Let's see, it's, you know, variable up to 1.25 to 26 volts. But that's out of Hazen, you know. All these images are going to be out of Hazen. I can't tell what the current is, but 40 microhenry inductor. Again, I pretty much bought all the parts for it, but yeah, but I can't really tell. Let's see. And it says a 5 amp. You know, expecting up to 5 amps, so that tells you something. So it's a variable supply with 5 amps. It's based on op amps. So we had this other one, which, you know, we've reviewed some of these circuits. So this is just my big collection of circuit photographs from textbooks. That's why I like having PDF textbooks. You can get way better pictures out of them for your notes. You know, these are all out of Hazen. Okay, this is, well, that's a function generator I was considering building. Varactor tune VCO, you know, so I covered that. Just didn't quite work right, but worked in a weird way because I put the wrong components in it. You know, here's this power supply. This is the one I believe the damn 741 out of, you know, by trying to charge a capacitor like I talked about in that other video. Oscillator, inverter, there's some circuits like this in there. I never entertained any of those too far. And a shunt regulator, which, you know, one thing nice about a shunt regulator is they are inherently short circuit proof. So you don't have to worry about it, you know, drawing ever more current than it's actually already using to begin with, but they're really inefficient. Okay. We're talking about switching regulators here, so we just, you know, which is appropriate. And then we got this power supply. Again, this is a different power supply in the same book on page 770. So I was thinking of building two, but I was like, that's kind of redundant when that other one, you know, because this does 25 amps, so maybe this is the one I was going to build. I don't know. I'd have to look. You know, because that sounds way more impressive from 3 to 27 volts output, but, you know, 25 amp, I mean, must be a hell of a transistor, huh? You know, quite a transistor to handle that. But, yeah, it is a switching regulator, so who knows. But, yeah, that's pretty much the end of the show there on that, so. But yeah, anyway, I you know, that's why, like I said, I'll be looking at some of this stuff closer later, but right now I just don't feel like any unexpected headaches. I just really kind of want to wrap this study program up, and, you know, that's what I'm doing here. This is the end of the show on it. But at any rate, you know, like I said, he does have, you know, tutorials on you know, Buck Boost as well. Now the problem is his video link is broken up. I've looked all over the damn place. What the fuck is, go fuck yourself, fucking mother. You know, I can't find a video actually on this. This is actually his first video on the buck converter, so but at any rate, you know, you can build the circuit though and kind of follow along, you know, if you want. So, you know, he's got all the code and everything you can download for it. You know, you see here. So, so like I said, if you want to do that version, you know, be my guest. And there is another tutorial he has. Basically for flybacks. You know, I had to dig for this, so go fuck yourself. Go fuck yourself, Google. Anyway, that's how he makes his money and everything, but still, it's more annoying than anything else. Not showing me anything I'm interested in. Shows you how well they track me. Let's see, but yeah, I mean, it's like I said, you know, he does have a video with this, so, you know, you can see here, you know, it's this flyback converter video.
If you ever opened a power supply of some,
but anyway, yeah, you can find it on his channel. Just gonna kind of dig for it, but you know, just look for flyback DC converter on, you know, search his videos on his site. You know, just search his videos. Let's see for, because I'm sure he has a link to this page in his video, and you can probably find it just on his site there. Just do some digging around in it. But you know, you can do a search it. Find it. Okay, flyback. You know, here we go. So, you know, this video, you know, pretty much covers that topic, and you'll click on
if you ever opened a power supply of some sort.
Same video. Click on more, and then, you know, he's got, you know, links to, you know, these tutorials and everything that I just showed you. So, you know, that's one way to go about finding it. You know, because again, I had to actually dig to find this, so anyway, but yeah, I couldn't find a video on the Buck Boost, but anyway, but I think that'll about wrap it up, so cheers.